Hey guys, welcome to another Chem Complete episode for the General Chemistry series. I'm Professor Tomney. I'm your instructor. So if you missed the previous lesson, I would suggest that you go back and check it out. It was an introduction to general chemistry, along with a general introduction to matter, atoms, substances and compounds, elements, things like that. And that's going to be important for continuing this lesson. So the first thing I wanted to talk about today, since we've already discussed substances and compounds, is the idea of mixtures and what is a mixture, and then basically there's different types of mixtures that we want to classify. So when we talk about mixtures, mixtures are nothing more than a combination of two or more different substances, right? So if I have a container and the container has water and nothing else, that would not be considered a mixture because water is just water. It's one substance or one compound. Now, if I turn around and I take a container of water and then I put a bunch of salt into that and I shake it up, now I have salt, sodium chloride, along with water. And the two of them have come together in order to create this mixture. So now I have a mixture. So there's two different types of mixtures. And we'll go ahead and we'll write this down on our whiteboard here. So the two major types of mixtures that we consider are, let me make sure I'm in black ink here, homogeneous mixtures and heterogeneous mixtures. Okay, so what's the difference between these two? So the main difference, because they both are mixtures, they both contain two or more substances, is that when we deal with a homogeneous mixture, the homogeneous mixture is going to be a mixture that is uniform in substance makeup, and you could really leave it off at that point. You could say a mixture that is uniform in substance makeup. However, I usually like to add a uniform in substance makeup when sampling. Okay, so it is always uniform in its substance makeup. However, the idea of sampling gives the best understanding of this. Okay, now when we deal with heterogeneous, this is going to be somewhat the opposite here. Now we've got a mixture, and all you have to add is not uniform in substance makeup, right? In substance makeup when sampling. So think for a second if you could come up with an example of a heterogeneous and a homogeneous mixture. Okay, so a homogeneous mixture, what we're saying here is that if I have a container that's got a sample of some sort of mixture, if I take 5 different samples, or any number more than one, and I take sample 1, sample 2, so on and so forth, so I line up all 5 in front of myself, right? So zoom in on this. And I line up all 5 of these samples in front of myself. If I could somehow analyze these samples in terms of the material makeup that's in each sample, if the original mixture that I took from was homogeneous, every single sample should be identical provided that I'm pulling from the same container, right? So for instance, if I took a sample of air, the air that we breathe, it has a certain ratio or makeup of, about 70% nitrogen, about 21% oxygen, and then there's a couple other gases in there that help make up the rest, whether you're dealing with carbon dioxide or what have you. If I took a sample of air, a large container full, and then I took 5 smaller vials from within that sample, somehow I pump the gas into these vials, and then I check the makeup of each of these vials, every single time I should come out within a very small margin of error with the same amount of nitrogen, the same amount of oxygen, the same amount of carbon dioxide, the same amount of argon or whatever other inert gas might be in there. They should be the same in every single sample because it's homogeneous. It's uniform in its makeup when I'm taking from this. So another good example of this would be any type of salt that's dissolved in water. So if I took a couple grams of table salt, sodium chloride, and I dump it into water, I mix it up very, very thoroughly so that the salt dissolves, and then I let it settle, and I take 5 samples from that, and I analyze the salt content relative to the water content in each sample. They should all come out to be the same, because the salt's going to spread equally through the solution. And we'll have lessons on solutes and solutions and solvents and all that kind of stuff down the road. But for right now, what's important to understand is that when I take all of these samples, they come out equal in their makeup. Now, not everything is homogeneous. There's certainly heterogeneous mixtures that you could have. So a good example I like to give students so that they can help in terms of their conceptual understanding of this is, imagine everybody usually knows what M&Ms are, the type of candy. So when you get M&Ms, you can usually, if you buy the regular type bag, not the holiday season or whatever, but that could still work, you get a bunch of different colors, right? You get red and brown and yellow and blue and green and all these different colors. So if I take an M&M, and let's say that even the factory did a good job in making sure that they did, you know, I have a bag with 500 M&Ms, it's 500 red, 500 green, 500 blue, so on and so forth, right? I get 500 of each. So technically speaking, statistically, if I mix this up well and I grab a handful, I should get equal amounts. But that's still not going to be the case. It's not going to be guaranteed. When I take one handful, I may get 5 reds and 3 blues and 4 greens and 7 browns, and then I take the next handful, or I put those back and I take another handful. I'm not going to get the same ratio each time, right? Or if I took maybe some people collect their change. You've got pennies, nickels, dimes, and quarters, and you put all that change into a big container as you're collecting it. Even if you had equal amounts of each coins and you shook them up very well so they were equally distributed. If I go and I grab handfuls of these coins every single time, I'm not going to get an equal number of quarters, dimes, nickels, and pennies. I may, by fluke, it may happen once or twice, but there's no guarantee of that like there would be with the homogeneous mixture. So this can be applied. Those are sort of outside examples, but this could be applied in chemistry as well. If I have a mixture of several solid compounds, and I sort of take them together and I mix them up really well. So I have some crushed solid phosphorus and sulfur, and then I've got some graphite, some carbon, and I put all that in and I mix it very well. Technically speaking, now there's maybe some margin of error, I still shouldn't get the same exact amounts every single time that I draw those samples. They can vary in their makeup, because I could get a little bit more graphite in one sample than solid sulfur in another sample, right? So that's the difference between homogeneous and heterogeneous mixtures. A homogeneous mixture is uniform in its composition throughout the entire solution, whereas a heterogeneous mixture is going to be one that, even though it may look like it, it is not uniform in its complete composition every time I take samples of it. And that's why I kind of add the sampling part, because you could have technically a heterogeneous solution that's mixed together very, very well, so that statistically you should be drawing close to the same amount, but there's not the same guarantee that you're going to get that, right? So that's the difference between those two. All right, so that covers mixtures. The next thing I want to talk about are properties and changes. And we really, when we talk about properties, we break them down into 4 different types. There's 2 major ones and then 2 additional ones that we'll talk about. And then on the heels of that, we'll talk about changes. So the 2 major types of properties that I want to start with are physical and chemical properties. And a lot of students have trouble separating these two when they start talking about them or thinking about them. So, for example, many students will think that boiling points are considered chemical properties, right? Because water has a different boiling point than, let's say, isopropyl alcohol that you have, that evaporates quicker, the type that you would keep in your medicine cabinet, because they're different substances chemically. And that's true, they are chemically different. But it's not a chemical change or a chemical property when you talk about boiling point. That's a physical property. Okay, so how do we differentiate between physical properties and chemical properties? And the answer is whether or not the substance that you are looking at has undergone some sort of a change in its chemical makeup. Okay? So if I'm checking a property, or I can observe a property where there has not been a chemical change in the substance I'm examining, that would be considered a physical property. All right. So boiling point, if I take water and I put it on the stove and I take a thermometer and I check the temperature at which it starts boiling, I'm checking the boiling point. That's a property of water. What temperature does water boil at? That's a physical property, not a chemical property, because even though water may be changing states, right, from liquid to gas, that's a physical change. Going from liquid to gas is a physical change. You're changing its physical state. It's still water, right? Liquid water in the pot, and then vapor, the water vapor. If I were to capture some of that vapor coming off of the top of the pot, that would still be water. If I ran it through and I analyzed it with some sort of test, it would still be H2O. It would not be a different chemical substance, right? So that's how you can tell if you're dealing with a physical change or a chemical change. So melting points, right, where water melts at 0 degrees Celsius, melting point, boiling point, all that stuff, those are physical changes. Those are physical properties that I'm observing. The melting point and the boiling point are called physical properties. The act of melting, the act of boiling, is a physical change. Okay, so those two, again, the big identifier here is, have I changed the chemical components or the chemical identity of the substance that I'm examining? Now, chemical changes, you do look for a change in the chemical outcome of the substance after you've gone through a chemical change, or what we would call a chemical property. So one of the most common chemical properties is flammability, right? Can something basically combust, or can we catch it on fire in the presence of oxygen as a fuel? And so combustibility or flammability is considered to be a chemical property, and the act of burning a substance is a chemical change. So, for instance, when you are at home, if you have a gas burner on your stove, you supply that stove with butane or propane or whatever gas you may be utilizing for your gas stove, and when that gas is burned in the process of heating or cooking or whatever you're doing, the outcome, the end point, is going to be different than what you originally started with. So as I'm combusting this butane gas or whatever it might be, I'm getting other carbon gases, carbon dioxide, methane, whatever might come out of it, okay? I'm getting new chemical compounds that are different than the butane, right? I'm not just changing the physical state of the butane. I'm not saying this is butane gas, I've now turned it into butane liquid, all right? What I'm doing is I'm actually combusting the butane into a new chemical form. And so when you deal with something like burning wood, which is going to be primarily carbon-based, okay, as a fuel, if I burn that wood into a pile of ashes, I have a new chemical makeup, whatever has come out of that. When I'm burning it, some of it may be released as carbon dioxide, carbon monoxide, but it's no longer the inert carbon that's sitting in the wood. It's turned into a different chemical structure, a different chemical formula. And so that is a chemical change when I'm observing that. Okay, because I'm ending up with a substance that's different in its chemical composition than the original substance that I had. Very important to be able to distinguish between those. So hopefully this makes sense when you're looking between those two. And again, I like to post review sessions, and so we will post one for the opening general chemistry lectures. And among those, I will ask you the differences in mixtures that we just talked about, along with physical versus chemical changes / properties. They kind of go hand in hand. Now, while we're talking about properties, because we just talked about physical and chemical properties, one of the other things that's important to consider are there are things that are not really classified as physical or chemical properties of a substance so much as what we would call an intensive or an extensive property. Sometimes you may call it an intrinsic or an extrinsic property. So what is an intensive property? An intensive property is going to be one that does not depend on the amount of substance that is being measured. So it is inherent, it is intensive to the property of the substance you're looking at, Okay, so for example, density. Density, if you take a look at it, water has a density of, and density can change slightly depending on temperature, but usually around room temperature, the density of water is going to be 1.0 grams per milliliter, and that's not going to change. So I could have a glass of water, I could have a swimming pool of water, I could have 3 drops of water, I could have all sorts of different amounts of water, but the density of that water will always be 1 gram per milliliter at a given temperature. Okay. Another good example, and we did talk about this with physical properties, boiling point. Water will boil at 100 degrees Celsius, right? And so whether I have a swimming pool worth of water, a cup worth of water, or a couple of drops of water, 100 degrees Celsius is the temperature at which all 3 of those samples will boil. That's the boiling point of water. Now, which one will come to a boil more readily or quickly? The 3 drops of water compared to the swimming pool. I have a lot less water, so I need a lot less energy to get that water up to that boiling point. But it doesn't change the fact that the boiling point is the same for all those samples. They all boil at 100 degrees Celsius. Okay? So that would be an intensive property. It doesn't matter how much of the compound I have. Now, for an extensive property, it does matter how much of the compound I have. So some very obvious examples of that would be mass and volume. Okay? Now that can be a little tricky because putting those together, mass divided by volume is density, which we just said is an intensive property. The ratio of those two will not change. Water, whenever you have a certain amount of water, it will weigh a specific amount in terms of its mass. Now, when we're looking at extensive, the mass itself or the volume itself, I think you can very readily see, does depend on the amount of compound that's present, right? So if I want to talk about volume as a property of a given sample that I have, well, that depends on how much of the sample I have. Going back to the water example, if I have a swimming pool full versus a glass versus a tiny little, container that can only hold a couple of drops, well, the volume of the swimming pool, I'm going to have a lot more water there than I'm going to have in the glass. And in the glass, I'm going to have a lot more water there than I'm going to have in the tiny container that can only hold a few drops. So volume and the mass, the actual amount of matter in each of those samples, does depend on how much is there. The more water I add, the more volume that water will occupy. Okay, so extensive properties will depend on the amount of substance that's present, whereas the intensive properties will not. So again, going back to those samples, the volume changes in each of those situations, but the temperature at which that substance boils does not change. Water is water is water. Different amounts of water, absolutely, extensive. Boiling point of water, intensive, because assuming they're all in the same situation, we're not changing elevations or other things like that that could affect boiling points. If I have 3 different amounts of water or sample sizes of water in this room, they're all at the same temperature, they're all exposed to the same environment, they boil at the same temperature. That's intensive. It doesn't matter how much I have in my samples. The volume, it does. That's extensive. So hopefully that makes sense. So to wrap this up, the last thing I want to talk about, there are a couple of, well, there's actually many ways that you can separate mixtures, okay, depending on their properties. And you tend to learn more of these in organic chemistry as you start to talk about different ways to separate out organic compounds. But it's important to be exposed to them at this point. There's lots and lots of different ways. So some of the most common ways, if you have homogeneous mixtures, which usually, not always, but usually tend to be gases or liquids, especially, it's very common with liquids. One of the ways that you could separate out liquids from one another is through the method of distillation, and that uses physical properties. You utilize boiling points when you distill something. So you set up what's called a distilling pot. It's a flask that has the 2 liquids you'd like to separate from one another, assuming that they both mix with one another equally. They're homogeneous. And then you can start adding heat. You're going to boil one of the liquids off into a gas phase, the one with the lower boiling point, before the other one that has the higher boiling point. As that gas starts to leave the solution, you can recollect it and it can drop off into a separate flask where you basically run a cool environment to recondense that gas and collect the liquid form, and you've separated the two liquids. So one of the common places we always hear about distillation is in the alcohol industry. They'll say something's triple distilled, or whatever. That's their seal of quality. That's how they try to push that they're they've done a good job with their separation. They're separating the ethanol away from other impurities, the drinking alcohol. And so the number of distillations they run through, they're taking the ethanol, distilling it away from other impurities, then taking that ethanol, distilling that away from any of the impurities that may have made it over again and again and again. So the more times you distill, the higher the purity of that ethanol that they use. Now, you do not get 100%. This actually is a good example. You do not get 100% ethanol when you buy a bottle of liquor. They do sell, I think it's like Everclear or whatever that stuff is. But generally, when you deal with vodka, tequila, anything like that, you're dealing with a mixture of a homogeneous mixture of alcohol along with other components. So vodka is one of the easiest to work with because vodka is nothing but water and ethanol. So good vodka uses probably purified water and has ethanol that's been distilled away from impurities multiple times. You mix the two together. If you look at a bottle of vodka, you cannot tell that there's more water in one portion and more ethanol in another portion. The mixture, we say it's miscible. They mix together very readily to form a homogeneous mixture. If I take 1 ounce of that vodka, another ounce, all of them should be approximately 40% by volume ethanol and 60% by volume water. That's usually the going amount for most vodkas. Some are a little bit higher. So that's distillation. You can also use filtration, which is very simple. If you have a solid and a liquid and you want to remove the liquid from the solid, you can filter it. You can set up something where you get basically a trap that collects the solid material. You use some filter paper or something, and then you suction away the liquid beneath and you collect it in a flask. You filter the two. Filtration is another separation method. You may hear of decanting, which is to simply pour off the liquid and try to keep the solid behind in a flask. There is extraction. Extraction uses two different liquids of differing polarities, okay, which is a new term that we talk about. But basically, think of something that won't mix with something else. So, for instance, when you have salad dressings, right, you've got the liquid portion, you have the water portion on one and the fat portion on the other, and they separate out into these two layers. You can do the same thing in chemistry. You can pick out two different liquids that have basically they won't mix together very well. They have what's called different polarities. And then if you wanted to separate out two solids that have different polarities, you could mix them into those liquids so that the solid that is highly polar will dissolve in the liquid that is highly polar. The solid that is not that polar will dissolve in the somewhat non-polar liquid. And then the two liquids, you can separate them out, evaporate them, and you get the two different solids back from one another. They're separated now. So that's extraction. Extraction is a little difficult to conceptually understand until you start utilizing it. But that's pretty much it. There's a lot of different separation methods. I mean, we're just barely cracking the surface here. I think that's where I'll cut it off because I don't want these videos to run much more than usually 25 minutes. I try to keep them to half hour or less for my lectures. So, again, mixtures, homogeneous, heterogeneous, physical changes, chemical changes, physical properties, chemical properties, intensive and extensive properties, and different types of separation. Okay, so make sure that you're studying this stuff. I will see you guys for the next lecture where we are going to start talking about the different units of measurement, which we call SI units. So how do we determine mass, volume, all of these types of things, temperature, time. There's set units that we all agree upon as chemists that we're going to use, which is the metric system. So we'll talk about those, and we'll also talk about some general conversions next time, because a lot of students get confused with a milliliter, right, versus a liter versus a deciliter, or a kilogram versus a gram versus a milligram versus a microgram. What do all these terms mean, and how do I mathematically sort through them? So we're going to get started on some math next time. So you may want the scientific calculator, piece of pen and paper to get ready for that kind of stuff. So I will see you guys there. Thanks for watching as always. It always helps if you hit the like button if you found this helpful. Comments, I'm happy to respond to them. I'm definitely here for you guys. And if you subscribe, you will get access to videos as soon as they come out. And it's the best way to stay up to date with the channel. So thanks a lot, guys. Take care, and I will see you for the next lecture.